You're about to see that it's now possible to transmit moving images over HF radio. Hello folks, this is Chris Long VK3AML. Standard definition analog TV requires 6 MHz of video bandwidth to transmit a 625 line PAL picture. But this video that you're looking at the moment is transmitted in less than 1/1000th of that bandwidth using a webcam conversion program devised by the Sydney experimenter Gary Millard. But of course you have to greatly reduce picture definition and frame rate to squeeze this requisite bandwidth. This picture is just 32 pixels wide by 48 pixels high, and it's scanned at 6.25 pictures per second, just 6 pictures per second. This is about the best one can presently achieve with moving images on HF radio. A moving picture phone thumbnail image in black and white. But I think you'll agree that there's sufficient here to give an image that's recognisably me with a sufficiently good illusion of movement to be convincing. At 4.8 kHz of bandwidth, this image occupies less than even a high-quality sound signal would. The video bandwidth calculation for a conventional line-by-line scanned image is fairly simple. It's the number of horizontal pixels in the image multiplied by the number of vertical pixels in the image, which we then divide by 2. Now why 2? It's because as the scanning spot runs over 2 successive pixels, one black and one white, this generates 1 cycle of video waveform. So now we have the number of video cycles per image, and we multiply that by the number of pictures per second. In the case of the Head and Shoulders image we've just seen, which is reduced in pixel count and in frame rate to be still recognisable, we have 32 by 48 pixels. That's 1,536 pixels per image, or 768 video cycles per picture. We multiply this by 6.25 pictures per second, and we have 4,800 cycles per second, 4.8 kilohertz. But this is a very difficult sort of waveform to transmit. You'll see from this waterfall graph, this spectral analysis graph of our 32-line picture, that we have to amplify all video frequencies from the frame repetition rate, 6 Hz, up to 4.8 kilohertz. Now to do that you need a specially designed transmitter because most voice transmitters are not designed to take very much modulation below 300 Hz. Okay, so we need a purpose-built exciter. That makes it difficult enough. But we also can't transmit this on conventional carrier-suppressed sideband because the carrier and its phase relationship to the video modulation gives the shape of the waveform in order to reproduce it correctly. So you can transmit this type of video on AM only, or to reduce bandwidth you have to transmit this by a technique called Vestigial sideband modulation. You use a square-topped filter, you shift it to one side of the AM-generated signal, and you transmit a slightly reduced carrier at 0.7071 of the sideband's filter maximum pass. Now this is achievable also with a purpose-built exciter, but it would be much more easily possible by using a software-defined transceiver with appropriate software to generate this type of signal. And I feel that we'll see a lot more of this type of moving picture slow scan once software-defined transceivers become common. Tonight we'll see several interesting alternatives that have evolved out of existing analogue slow-scan TV for transmitting images and other material on voice channel radio. All of this is reliant on the combination of computers with radio transceivers, providing facilities in combination that neither device had on their own. Let's go back to a 4K camera to see what we have to offer tonight. Here we are, several megahertz wider, in living colour, 1080p at 25 pictures per second. Every blemish, every zit faithfully reproduced, and they call this progress. Now, let's have a look at the historical evolution of transmitting narrow bandwidth pictures on HF radio. To transmit greater image definition than the 32-line image you've seen, you have to extend the transmission time of each image to several seconds or even tens of minutes. And then to see that reconstructed image, you have to employ some form of image storage as the picture is slowly reconstructed. With television, repeated image transmissions do this trick through persistence of vision of the eye. But longer transmission times require physical or electronic video signal storage. In the beginning, back in the 1920s, there was phototelegraphy, or what we now call radio fax or weather fax. A negative picture was wrapped on a rotating glass cylinder and was scanned very slowly by a finely focused light spot, transmitted through the negative onto a photocell. At the receiver, the amplified current from the transmitter's photocell was fed to control a modulated light, focused onto a synchronously rotating receiving cylinder, rebuilding the image. The storage on the print paper was provided by the photographic action. This, for example, was the first fax picture sent from Melbourne to Sydney, as far back as August 1929. It took more than 7 minutes to scan and transmit this initial commemorative picture. Since World War II, HF radio fax has been commercially used in Australia to transmit the latest weather maps to ships at sea. Today, computers have replaced the original mechanical cylinder fax receivers, and computer memory is used to store and reassemble the scanned image on a computer screen. There are 2 Australian weatherfax transmitting stations involved. One, VMC at Charleville in Queensland, serves our east coast, and the other, VMW at Wiluna in Western Australia, serves the west coast. These images were received here at VK3AML, and you can hear the sound of a fax transmission behind me. The transmission mode is a varying, very narrow bandwidth, frequency modulated audio tone. This system avoids a lot of the image degradation of fading and multipath propagation suffered by amplitude modulated tone systems. In this FM system, which can be demodulated on a sideband receiver by tuning to one side of the fax signal carrier, black is represented by a 1500 Hz tone, white is a 2300 Hz tone, with the various shades of grey in the picture falling between 1500 Hz and 2300 Hz. Sync pulses are transmitted at 1200 Hz. Mechanical HF radio fax was standard until 1957. But in that year, a student at the University of Kentucky, Copthorne MacDonald, W4ZII, made the first entirely electronic fax system, using war surplus radar tubes to store pictures for viewing. Long persistence radar screen phosphors could retain their image in screen glow just long enough if the screen was scanned once every 7 seconds. This was television of a form, but it was slow scan television. Using standard fax frequency modulated audio tones to carry the picture and a 3 kHz voice channel, the 7-second scan rate allowed an image of just 120 pixels by 120 pixels, black and white. On photos taken by time exposure, the pictures were, well, acceptable, but to the eye, it had to be admitted that the results produced were fairly poor in reproduced grayscale. As you see here, by the time each image had scanned to the bottom of the picture, the top was fading out, and the colour was a sickly yellow-green. When these monitors were made commercially around 1970, they cost about $800, the equivalent of about $3,000 today. So this was a mode only for the advanced home constructor or for the wealthy. Australian pioneers in this field around 1970 included the late Mac McKibben VK3YEO, Gil Miles VK2KI, Doug MacArthur, then VK8KK in Darwin, but most of all, the EMDRC's former president, the late John Wilson, VK3LM, literally known as Mr. Slowscan. Even when TV scan converters for SSTV with the first RAM chip memories became available around 1976, the results, as you see, were not that much better. In 1972, the late Dan Van Alken, VK3UI, and I decided to improve on the system if we could. Given a narrow video bandwidth, how low could you take the pixel count to retain a recognisable human face? How high did the scan rate have to be to achieve just apparently moving pictures, rather than just mediocre stills? We discovered that somebody had achieved precisely what we were aiming at, moving pictures of this quite acceptable standard, without even using expensive high-voltage cathode ray tubes 40 years earlier. The name of this man was John Logie Baird.
It is now 12 years since this apparatus showed the transmission of outline images to the public for the first time. This is the scanning disc with its lenses. This is the second disc by which the light is further divided and passes into the light cell. This apparatus was shown to members of the Royal Institution and others on January 27, 1926, and showed true television images in light and shade for the first time.
Baird conceived a Nipkow optical scanning disc system to transmit optimised moving pictures of limited definition over a medium wave broadcast band voice transmitter. A disc with a spiral of lenses or holes swept the image line by line over a photocell shown here in yellow. The video signal from the photocell was hugely amplified and transmitted to a radio receiver whose output was fed to a modulated neon lamp. Viewed through a receiver disc synchronised to the camera disc, the picture would be reproduced. Here's Baird with the system operating in 1927, dummy head for a subject, and the reproduced 30-line TV image. Dan VK3UI and I built a similar camera. 56cm scanning disc with a spiral of 48 holes, spun by a sewing machine motor at 300 RPM. 12cm magnifying glass for a camera lens, and 600 watts of hot lighting within 2 feet of the person to be transmitted. Inside the camera, a germanium OCP71 phototransistor, more sensitive to infrared than to visible light. Our receiver was a similar 48-hole disc with a valve amplifier modulating a big war surplus neon lamp, viewed through the scanning disc via a magnifying lens. The receiver disc was synchronised with the camera by manipulating a power potentiometer in series with the mains. It was all very crude, but enough to show proof of the concept. My photo was taken just before my 18th birthday in my Camberwell High School uniform. Really, what a dreadful nerd. But could it produce an image? Could we transmit it on 160 metres? And could we record video on an audio recorder? My only recorder was this mono-audio, battery-powered 5-inch open reel machine with a frequency response only from 100 Hz to 6 kHz. It had a DC motor with a centrifugal governor, forever hunting up and down in speed, so the recorded video would be unsteady. I'd spent 6 months of 1971's Sunday afternoons at the State Library of Victoria, studying ancient engineering texts on the dead technology of optics and mechanical scanning, video amplification and light modulation. I'd written to Baird's surviving colleagues for information, and to Gil Miles, VK2KI, another television pioneer. Dan Van Alken, a first-year engineering student at Monash, introduced us to RC coupling time constants, passive equaliser design and video signal amplification. It was February 1972. We hooked the camera to the mic input of my audio tape recorder. Dan ran the camera up to speed, and this is the first time I've ever shown those results publicly. That's the 17-year-old version of me, jumpy and blurry due to tape speed flutter. The infrared response of the camera made my hair look white. Horizontal edges were jagged owing to inaccurate hole cutting in the scanning disc. But yes, we could transmit fully moving pictures in 5 kHz of bandwidth. We were ecstatic. Then Dan took my place in front of the camera. Not quite so clear. The OCP71 had heated up and it was getting noisy. Dan VK3Y, I should say, was the most brilliant, creative and affable young engineer that I ever met. He was diagnosed with a brain tumour at the age of 25, and until it killed him 11 years later in 1988, he became progressively more debilitated. Life isn't always fair. Dan and I did many tests after midnight on 160 metres AM with this camera and Dan's clamp tube modulated AM transmitter early in 1972, gradually improving our pictures. Then we took the gear around the radio clubs, EMDRC, Wandsark, Moorabbin, even the Camberwell Youth Festival, collecting signatures to support us in getting a formal permit for on-air tests. What I'm about to say may offend some people, but this is something that's necessary to understand what subsequently happened. Dan and I were invited to present our request to the WIA committee at Victoria Parade, presumably to support us in our request to the PMG for tests. At this gate, a man named Cyril blasted me for breaking the law in building a closed-circuit TV system. I finally got past this nonsense and into the meeting, presenting signatures, giving a broad view of the theory, summarising what we had achieved and what we wanted to do. The puffed-up, obstructive ignorance, condescension and dismissal that followed absolutely appalled both of us. They said it's impossible to transmit video on HF, it's illegal, you'll take up the whole of 160 metres, you'll create a nuisance. One of them even claimed that we were lying about our results, that it was impossible, and that mechanical television was a proven unviable technology. We were shown the door. We actually weren't directly interested in mechanical scanning. We just wanted to check viability with this simple equipment. And beyond that, for years afterwards, I heard these same geriatrics belittling our efforts on the air. As a result, I lost any desire to get a ham licence for the next 34 years. In that time, most of my operating was on modulated light beam systems, didn't have to be licensed, they were of my own invention, in avoidance of radio. Anyway, Dan VK3UI and his friend Tony VK3AML were very willing to provide their AM 160 metre transmitters for TV tests. Advice to the young today. If you want to get a permit for experimentation of any type, digital, analogue, whatever, go straight to the ACMA and Spectrum Management, the professionals. Don't deal with amateur bodies, institutes, clubs or self-interested gatekeepers. And never belittle teenage experimenters. Their minds are probably more agile than yours, and they remember unjustifiable nastiness as we did for a very long time. These days, young folk are adept with a level of digital technology that most hams over 50 don't even know exists. They'll put you to shame unless you embrace their expertise. When foundation calls were finally free to use digital modes this year, our Easypal digital slow scan group had a huge influx of young folk, more adept in computers and software than any of us, and we're delighted that they've come. We went ahead with 160 metre tests at odd hours and kept a low profile. In 1973, Dan and I designed an electronic analogue of our old mechanical scanner, more complex but with far better picture quality in the same 5 kHz of bandwidth. This is Tony Sanderson VK3AML photographed from our monitor screen, a serious improvement. With a new stereo audio recorder, a Tandberg, we could record the narrowband video on one channel, synchronous sound on the other stereo channel. After a brief report in the prestigious British magazine Wireless World, a British experimenter with parallel ideas to ours contacted us, the Nottingham physics teacher DOUG PITT. We started exchanging narrowband videotapes across the world, like this.
Hello, DOUG PITT here, speaking from Nottingham on the occasion of the 26th meeting of the Narrowband Television Association. I hope that you'll find this recording interesting and a useful source of a video signal.
With DOUG PITT and others, we formed an association based in Nottingham, publishing a Roneo Ideas Sheet Bulletin, Volume 1 we called it. The circulation steadily increased. Then in March 1976, this grew into the association's quarterly magazine, with my system's circuit and a rough photo of me taken from the screen in the first issue. Membership spread out worldwide with creative input from many communications engineers, ham radio operators, television history buffs, computer programmers and mechanical engineers. As I speak, they've published 43 volumes of these yearly journals over a period of 44 years. In 1980, Tony Sanderson VK3AML transmitted this recorded video on 160 metres AM from Melbourne to the Adelaide home of John Ingham VK5KG, where we had tuned in.
Anyway, the Long's walking around the room looking for something, so we'll keep describing the system. Anyway, these scanning lines get focused onto one's face or whatever, and sitting just above the tube is a photomultiplier tube, which is being used to receive these missions. So the photomultiplier tube sees all these little lines scanning across your face, picks them up, amplifies them and chords them. Well, we're chording at the moment.
All of the narrowband video systems that you've seen so far require purpose-built modulation and transmitting systems. For those preferring simple plug-and-play software to use with a standard HF single sideband rig, Con Wasiliev, ZL2AFP of Gisborne, New Zealand, has cleverly devised a whole new method of transmitting TV images, but at the expense of slightly longer image transmission time. With conventional analogue TV, a single scanning spot traces out the image area in a series of line scans, usually left to right and top to bottom, like this. Con's software allots a separate subcarrier tone for each scanned line in the picture. The top line of the picture generates an FM subcarrier at 2.6 kHz. The bottom line generates an FM subcarrier at 300 Hz. The trick of Con's scanning system is that all of the scanning lines are transmitted simultaneously, like this. There's a separate scanning spot for each line. The multiple scanning spots shown here in red all generating their own separate FM signals simultaneously at different audio frequencies. Con uses 48 or 96 lines assigned to 48 or 96 subcarriers spaced between 20 and 40 Hz apart, a totally novel departure from any previous analogue TV concept. The real beauty of this system, as the spectral analysis graph of Con's 96-line video signal shows, is that the video energy is very evenly distributed across the transmit passband in 96 subcarriers spaced 33 Hz apart, and at frequencies that a standard sideband speech transmitter can easily handle. Very narrowband frequency modulation of each subcarrier carries the picture pattern. In fact, if you squint your eyes at this waterfall graph, you might see the outline of my face drawn in the frequency wobbles of the subcarriers. Compare this with the waterfall graph of the 32-line system narrowband TV that you've seen previously, which had video components down to 6 Hz, very unevenly distributed across the passband, with energy concentrations at harmonics of the frame rate and the line rate. And back to the spectral analysis of Con's system. This multi-subcarrier FM is fairly bulletproof to selective fade. If selective fade does occur, it tends to appear as diagonal noise bars on the picture, rather than completely disruptive loss of picture quality, as we'll see. The only problem is that because the modulation is FM, the transmitted signal can't be narrower than double sideband AM. The whole bandwidth is 2.2 kHz, and with guard bands between the subcarriers, the scanning speed is just too slow to produce true moving pictures. The 48-line system, seen here, transmits just 1 picture per second. Con's 96-line system, seen here, transmits 1 picture every 3 seconds. There are also similar colour transmission modes that Con has written software to generate, but these also increase the transmission times of the pictures. Con's system is more fast SSTV rather than true television. A few years ago, I got some British friends in the London area to transmit webcam images of themselves on 80 metres sideband, while I was monitoring them on a web SDR set up at Hack Green, 200 kilometres northwest of London. In Melbourne, I could intercept and decode the pictures perfectly from the WebSDR's internet audio stream. This shows what CONS software can do on 80 metres, where noise and multipath are often a problem. That presumably was Vic walking in front, and there's his desk with his computer. And there's Vic. That was a 48-line test. Now this is 96 lines. Well, I believe that's Vic Brown's arms. And there we're getting a look at the transmitting gear, which we're hearing this off Hack Green, which I think is about 150 miles, about 200 kilometres to the northwest of Vic. This is received off 3712.5 kilohertz on 80 metres. You'll notice the dips in the selective fades are marked by diagonal noise bars. And we have a phone call as well. Never stops here. The colour version of CONS 48-line software takes 3 times as long to transmit, 3 seconds per picture rather than 1 second per picture, as successive colour primaries are scanned. Red, blue, green, red, blue, green. The last option for pictures over HF radio is not specifically a slow scan TV or a video system at all. It's a sophisticated program for digital file sharing via an audio stream. It can be any digital file: JPEG picture, line drawing, spreadsheet, Microsoft Word document, text file, animated GIF. And because it's digital file transfer, the material is reproduced with zero noise or distortion. This program is the Easypal software package, at present the best and by far the most mature program for file sharing on HF radio. Easypal uses the Digital Radio Mondiale DRM multi-subcarrier system, which enables the data to be sent over a narrow channel, say 2.5 kilohertz wide, on HF or VHF frequencies with the maximum possible transfer rate of the data. It was devised by the late Erik Sundstrup VK4 Alpha Echo Sierra of Gympie, who died at the age of 79 in March 2015. Erik was formerly VK3OK of Macedon, who was involved with the aviation industry and was a pioneer expert software programmer. Fortunately, in November 2008, members of the Gympie Amateur Radio Club shot a video of Erik explaining the development of this software and its predecessor HAMPAL. Erik Sundstrup can of course explain it far more comprehensively than I could.
Yeah, just a bit of my background to start with. computing has been my hobby since 1973, and I started off programming at that stage, and I now have programming in Delphi. I've tried all the various languages, starting off Visual Basic, C, C++, and ended up with Delphi, which is a very, very good language. You can program at low level, etc., etc. 1973, I think I was the second person who had the AmTool board operating. Clive VK3RV got the first one. That was with Peter Martinez. I later collaborated closely with Peter when we made up another program, which was a digital program that made a great whir in the world for 4 days until a better one came out and they forgot about it. Set up the first RTTY repeater in VK3, and I made many, many programs: SSTV PAL, SSTV Multimode, PSK PAL, and I closely collaborated with Mako Mori of MMSSTV. Anyone work that slow scan television or know that program?
Yeah.
It's analog. Anyhow, Mako, he was a Japanese chappie, and at that stage you were buying all these programs for about $120 each. This is where we both became very unpopular because we released it as freeware, and that really upset a lot of people. Now, the first thing I came across the digital type of program that I've written now was originally written in Linux, and I was able to convert it over to Windows. But anyhow, just a brief background, the actual core of the program Easypal is a DRM core that was written in Europe by a lot of very clever people at the university, and then released commercially, and it was used for transmitting of data over bad telephone lines and things like that. Later on there was a very clever fellow called Cisco, HB9TLK, and he was able to turn the code into a DLL, which then made mere people like me able to use the various routines in it to make up programs like this. So I had a wonderful time making all these programs up, and about 3 years ago we were struck by lightning in the shack, which destroyed all my computer gear, destroyed all my wife's telephones, everything went. I lost all my software, and you might say I went into a bit of depression. So I didn't go near computing or programming again for a whole year. Lost everything, all those years and years of work. So I started up again with this particular program, Easypal, and it was probably a good idea because of all the mistakes that I made in the previous programs that I couldn't change. I've now been able to rectify that. Now it's a digital program, but a little bit different to the normal digital programs. Most digital programs run on what they call ARQ, where you have handshaking between two people, but it's only limited to two people in contact, like PACTOR or AMTOR, so it's not a fun group type of activity, whereas this is, because you don't have to, anyone can receive it. You can be in a group of 10 or 15 people and they can all receive the pictures and all talk to each other. And digital, of course, has got the great advantage that you've got error correction, which means that it's possible to get a perfect transmission, and that's what we can get. We can get, depending upon how much time you've got, you can have photographic material just amazing. You can look at the young girl there, you can send that in about 60 seconds. You can't possibly do that on other means. A little bit about the digital, why it's so good. Most digital signals, if you see them, see a myriad of carriers. You might have 16 different carriers. If you look them on a waterfall, which I'll show you there later, you'll see the carriers described. They're, say, carriers spaced about 100 kc apart, and they're all modulated, and there might be up to 16. And that will mean that if they interleave them, that if there's a static crash or someone talks in the middle of it, it won't destroy the information. So you can still get perfect error corrections or whatever. Now the big difference about this DRM mode compared with all the others is that where these carriers are limited to what bandwidth they have, and how high a baud rate they can sustain. So if the carriers get too wide and overlap, they all mix with each other and you have the gong. Now this DRM is the first one that now has carriers very, very wide that all overlap, and you can get huge baud rates out of them, and they work. They don't have any problem. The way they do that, they use a time lapse. So you only look at one carrier while you don't look at the other. It doesn't exist, so you can get, well, in this one you've got 57 carriers all running together. 57 carriers, all at different frequencies, all being modulated, all overlapped, and they're all sorted out. And you'll see that when I pretend I'm transmitting something from here over there, that you've got a little set of lights on the right hand side. You can see all red, a little line of red. And I've got various stages of the synchronisation to when I start transmitting the signal. So what can it do? Well, it's a file transmission type of program, and you can send any file, pictures, you can send text, you can send even exe files, and they can be received at the other end absolutely perfectly, not one single error in them. It's been used, there's so much in this program, it's difficult to explain all the sequences, but there's an email facility in it where you can send emails from, say you're in a caravan park and you have no access to the internet. You can use this program to contact someone who has, where you've set up the program to access your internet, and he can receive you and through you send out an email to someone, any on the other side of the world. They can then reply and it goes back to the guy in the caravan park. Now this has been used by Mars and some of the emergency traffic overseas. And the same with the text messages, because you can have very small text messages which have absolutely total error correction and very, very fast, and that's what's being used particularly in the States, which was rather interesting. They don't do it themselves. So here we are, a little back room in Kimpi. I guess I could go on and on with all the various things in it. I think the best thing to do now, there's not that much time, is that I'll start sending pictures and you can sit around close to that, and I'll try and explain what's going on while the picture is in progress of being received.
Unfortunately, Erik Sundstrup's video cuts out at that point, so I'll have to show you the rudiments of Easypal here on my computer. But if you want the full details, perhaps turn up on our 2-metre net of a Thursday night. You'd be very welcome. Every Thursday, 9 p.m. on 146.7, the VK3RML repeater, we have our Easypal net. There's usually about half a dozen guys there to transmit pictures and show you the workings of this program. But I'll just give you a couple of demonstrations here to show you how this works. The audio link between your computer sound card and your transceiver is important. Unless you isolate the earth of your computer from the earth of your transceiver, you can get a circulating earth loop producing hum and RF feedback through the audio lead. The easiest way of breaking that audio lead DC path and avoiding the earth loop is to use two 600 ohm 1-to-1 audio transformers. To operate at telephone frequencies, you can use something commercial from JCAR, but if you want a bit better audio quality, you could use two old audio coupling transformers from cast-off broadcast mixers. That's what I have here. I've never really bothered with a chassis. It's a bit like the rest of the mess that this shack consists of. But these large transformers give me a good audio response down to 30 Hz. Alternatively, you can use a commercial interface like this Signal Link if you have about $120 to $150 to spare. With Easypal, audio levels are fairly critical, so that potentiometer volume control is necessary, especially in breaking the line audio level down to a level suitable for the mic input of your transmitter. I recently added a small standalone Zoom H2 audio recorder to my interface so that I could log our slow scan transmissions. Okay, we've opened the Easypal program and there are several windows here. This window, the vertical one, is a waterfall display. That shows you the full width of the audio stream, 500 hertz there, 2500 hertz there, so that you can see the multiple subcarriers forming and coming down the screen. You can also, if you're using sideband, you can tune your radio to be precisely in the right demodulation area on this waterfall display. Above it, this graph in this little black box here is a frequency response graph of the received audio. Up here, this little thermometer is the bar which tells you whether your digital signal is synchronized to the demodulator inside the computer. And the actual picture, if one's to be received, appears in this big black receiving frame. So let's just activate an audio file. And you'll see my call sign there has been generated in the frequency domain. I'll turn that down a bit. There are 3 markers there, asymmetric, and they indicate whether you've got on sideband upper or lower sideband, so that you're demodulating this correctly. You'll notice that this is now turned green. I'm demodulating with synchronization, and this is indicating that the level is about right, and this indicates a signal to noise ratio of the signal of about 26 dB. Down here, this little horizontal thermometer is indicating how much of the picture has been received. It's getting towards the end. We should be seeing a result shortly. There you are. And in the space of something like 50 seconds, we've managed to resolve a picture there that is completely noise-free. Doesn't matter how much noise is on the path as long as you demodulate the numerical components being transmitted. And much, much higher definition than anything that you can achieve on analog slow scan. A particular problem that you may encounter with this is the situation where the thermometer doesn't reach the top bar. That generally means that this pattern, this Easypal stream, is being clipped. And usually this is an indicator, this red bar not being filled with green, is an indicator of clipping, excessive audio level. More level isn't always better. One particularly neat trick that you can do with Easypal is to transmit pictures and text on your waterfall. And you can imagine what people using software-defined receivers and looking at their waterfalls would feel when they see your face come up on the waterfall like this. With this Easypal program, we can also transmit many pages of text far faster than CW or PSK31. In fact, I could probably transmit an entire book on Easypal within about 5 minutes. I'll show you how long it takes us to receive a couple of pages of text. Again, the waterfall, the same. Synchronisation is indicated here. My level is about right. And this horizontal thermometer right above the start button is showing that the files are being received correctly. No gaps. And the text should be resolving about now. There we go. And you might be able to see Easypal text guide. I've actually transmitted by radio the guide to Easypal, and it occupies, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9 or 10 pages there of text that we've just transmitted in 60 seconds. Amazing, isn't it? One particular aspect of Easypal that doesn't get too much usage is its use to transmit very short animated GIFs or movie sequences. And in fact, I managed to heavily compress an animated GIF of myself. People who watch this will be excused for thinking that I'm excessively using myself as a model, but in this time of COVID, what else can I do? I'm the only person available here. But I'll transmit an animated GIF via Easypal, and this is something that standard analog slow scan just cannot do. Again, the call sign there. There's the graph of the spectral distribution of the transmitted audio. Thermometer there indicating synchronisation. And the first frame of the animated GIF is already there. Appears very small, but you can enlarge it. And there's the full file transmitted, and you'll see in a moment that it will move. There you go. Well, I hope you've seen that there are quite a few options these days for transmitting pictures and video on voice transmitters, both on HF and VHF. And I think that just as the 20th century was the century where ham radio operators building hardware had the edge, in the 21st century, probably the software makers will have the edge. Certainly as software-defined radios become more general with their flat-topped IF responses and their variable bandwidth at the touch of a mouse key, we'll see a lot more of these non-voice modes being used, I hope. Amateur radio in association with computers opens up all sorts of new possibilities that we can't even dream of. Just to close, I'm going to use that 7-letter, 4-letter word relating to ham radio, entertainment. It's supposed to be it's supposed to be illegal on ham radio, but I'd like to show you how entertaining a narrowband video can be, just as a test. I'm going to have some assistance from a man named Milligan to close this presentation, and this was also video recorded in a 6 kilohertz bandwidth.
10, 9, 8, 7, 6, 5, 4, 3, 2.
And now the late news. To be precise, an hour late. The Department of Energy say that by the year 2000, England could run out of Arabs. The Arts Council are to subsidise the National Youth Orchestra to the tune of Beethoven's Fifth. Good news for Bing Crosby fans. Tom Jones has broken his neck. And pop star Dee Denny, who married Mary Lee last week, are to be separated. Someone is going to chuck a bucket of cold water at them. And that's all from us for tonight. Good night.